If you have a simplicial complex, like here, coming from a graph, we can define two matrices. The first matrix is the connection matrix, which we see here. It just tells which simplices are intersecting with each other. So this is an adjacency matrix of a quiver. Now, the Dirac matrix is also associated to a graph. It just, you connect only two simplices if their dimension differ by 1. And that comes from the exterior derivative. Right? Gradient goes from 0 forms to 1 forms. Curl goes from 1 forms to 2 forms. Then there's the divergence, which goes from 1 forms back to 0 forms. It's a little bit nomenclature problem, because we have also divergence then going from 2 forms to 3 forms in 3 dimensions. But here we have the diff grad is the Laplacian, which is here the scalar Laplacian, which you usually have in calculus. But then there is the one form Laplacian, which is the Laplacian on edges, which is relevant in electromagnetism, for example. And then we have the Laplacian for 2 forms. In this case, there's only one triangle, right? So this is a 1 times 1 matrix. And we want to understand the spectra of these. We have talked a lot about this. A lot of work has been done for the Kirchhoff matrix, but you have also nice supersymmetry. Actually, both stories are absolutely fantastic, because we have here we have a symmetry and here we have a symmetry. So here the symmetry is supersymmetry. Not complete supersymmetry, but we have kind of the even forms and odd forms, the non-zero spectrum of the even and odd forms agree, which is absolutely fantastic. This allows to prove, for example, Euler-Poincaré formula. It allows you to prove the Lefschetz formula very, very elegantly by just deformation. And so this symmetry is very nice. It also gives you a symmetry of the spectrum of the Dirac matrix, which is negative and positive. So the antiparticle part is just completely symmetric to the positive part. But it's broken, the symmetry, in the sense that the zero eigenvalues are topological. The zero eigenvalues are just the kernels of the blocks. So in this case, we have just only one harmonic 0 form, no harmonic 1 form, and no harmonic 2 form. The Betti vector is 1, 0, 0. That's a contractible space. Now, there's also some topology coming in here on the connection case. I showed once that the number of positive eigenvalues minus the number of negative eigenvalues is the Euler characteristic. The determinant is very nice. It's just a product of the minus 1 to the dimension of x. And the Euler characteristic is the sum. Here we have the product, so I call this the Fermi characteristic ones. Especially the determinant is 1 or minus 1. It's a unimodular matrix, and the inverse of this matrix is integer matrix also. So we here see the inverse. That's the green function matrix. These are the potential energies between two simplices. And then you can add up all these energies, you can add up all these numbers, and you get the Euler characteristic. So the Euler characteristic is a natural, energetic interpretation. All these also works for higher characteristic, where you book characteristic for m equal to 2 higher characteristic, where you look at more general Euler characteristic numbers, and then there is a Euler-Poincaré formula. The same way you prove it by using the Hodge, by using this supersymmetry, McKean Singer symmetry. It's a very elegant mathematics here, and also here there are surprises. Now, for estimation, here in this case we can just also use the degree, so the eigenvalues are bound by just the degrees of the matrix of the graph which we have, and here also we can do that also. So matrices are simple enough that we can do that. You see there in this case we have just 1, minus 1, 0 matrices, and here we have 0, 1 matrices. The product is more complicated, and here the inverse also can be more complicated. It looks as if this is always 1 or minus 1, but in higher dimension especially, this is not. The open sets can intersect in a complicated way. This is kind of a little bit the surprise. I thought with this formula here this green star formula for many, many months because I did not think about open sets. Open sets are complements of simplicial complexes. And for open sets, the cohomology and everything works the same. I worked for this also for, a year, just understanding the kind of what happens when you put an open and closed set together. I call this the fusion formula. Here, it's a little bit more subtle. I still don't understand what happens really when you take open sets. Most of the time, you have zero. So, for example, you take a vertex here. For example, you take the open set of this point here, then you have just a 2 times 2 matrix, which is 1, 1, 1, 1, and determinant is 0. So this part here doesn't go over, but maybe there is something more, maybe there is some more structure hidden. I should also mention kind of something curious in the one-dimensional case. If you look at curves, you have no triangles, a triangle-free graph, for example, or a one-dimensional simplicity complex. And there is a connection between this story, because if you take L minus G, if you take L minus G, then you get the signless Hodge matrix. But that's only true in one dimension. I would love to have something like that in higher dimensions, but I didn't find anything yet. So that's an update about these two exciting parallel stories. Last time I called this the more bosonic story, and here more the fermionic story, because here in the fermionic part there is calculus coming in, and here there's just summation. There is no exterior derivative, exterior calculus coming in. That's it for today.